expectation, and then we can compute its expectation. So let's compute the variance of n of y equal to I of t. So let's compute. So what is the variance of, say, n of y given y equal to t? We're going to play the same trick. Okay. This is the same as the variance of n of t given y equal to t. But I know that n of t and y of y equal to t, n and y are independent random variables, so this must be same as the variance of n of t. And I know about the n of t that it has a Poisson distribution with parameter lambda t, so its variance is going to be equal to lambda t itself actually. So we know that for the Poisson distribution, expectation and variance are the same, which is lambda t. So hence I can say, as we did in the case of expectation, so the variance of n of y given y is going to be equal to the lambda y. And if this is the case, calculate its expectation. This would be same as the lambda times expectation of y. And expectation of y is really expectation of y is really t upon 2, because this is what y has a uniform distribution. So the variance of y is going to be this number, okay, plus this number plus this number. Okay, so you add these two, substitute them into this formula, and you have the variance of the number of people that really catch a train actually, that arrive on the on time. Okay, so this is what is one of the example on computing the expectation and variances through conditional expectation and conditional variance actually. Okay. Next, I'm going to move to a very interesting topic. So, up to this time, we have been calculating the expectation and variances through different ways, and we need to solve pretty complicated kind of integrals to solve what do you call to compute the expectation and variances, are the higher moments of the given random variable. And now we will like to get to what you call the heavens, or maybe the best way or the easiest way or the most interesting way to compute the expectations, variances, and the higher order moments of the higher order expectations of the given what do you call random variable actually. Okay. So here's the thing. Let's call moment generating functions. So as by name, this is going to be a function that generates the movements actually. By the movement I mean, this is the first movement of the random variable, this is second movement of random variable, and this is the nth movement of random variable. So these are called the movements of the random variables actually. The question is, can I have a formula for calculating these movements directly without getting into the very complicated kind of calculations? The answer is yes. If you know the movement generating formula for the given random variable, you can easily calculate these actually, okay, through that movement generating function. So what is the definition of movement generating function? So suppose x is a random variable. Suppose x is a random variable with follows some distribution. Then moment generating function mx of t is a function okay, that is defined as computing the expectation of Tx. Okay, so compute the expectation of Tx. So if you know the distribution of x, you can compute the expectation of Tx. Then this expectation is really the moment generating function, which I'm going to tell in a moment that how this expectation will allow you to compute any moment that you like actually. Obviously, in case of discrete random variable, the moment generating functions is going to have a definition. So it's going to be expectation of e to the Tx. It's going to be a sum that takes the value x. Okay. So if x takes the value x, you need to compute the function at these values multiplied by the probability that x is x. In other words, the PDF of it actually. So compute this sum and you have the moment generating function. And obviously in the continuous time case, so what you need to do, you need to integrate from minus infinity to infinity what? E to the Tx, okay, times the PDF of the random variable x actually, okay, of the random variable x. So this is going to be really the moment generating function for any given function x actually. Now, if we know this function explicitly, why it is easy to compute the expectation and the variances actually. Okay. Why it is easy to compute the expectation and variance? And the answer is yes actually, it's not difficult. Now if I compute, for example, the first order derivative m prime of x of t of this. So this is like differentiating t, the expectation of x with respect to e to the Tx actually. This is what that you're going to get. Okay. By the way, you can see that if you, for example, differentiate this sum with respect to x, with respect to t, then the derivative of the sum is going to be the sum of the derivatives actually. So in other words, if I compute, for example, d by dt of this sum, then this is going to be the sum of the derivatives actually. Okay, sum of the derivatives. Though there is a cheating in it, because if it has infinite values, then you have to be careful, you know, when you are doing these computations actually. Okay. Anyway, this expectation is a function of x actually. Okay, it's a function of x. It depends on x. So if you are integrating with respect to x. If you are taking sum, you are taking sum with respect to x. While this derivative is the derivative with respect to the time. So for example, in this integral, if you differentiate it with respect to time, and this integral is with respect to x, then you know this derivative is not going to put any impact on the integral. If you wish, you can take it inside and derivate it, okay, and derivate the functions inside that actually. Okay, so what do I mean by that? The derivative of the expectation is really the expectation of the derivative. So if you wish, you can take this derivative inside, because these expectations are relevant to the function x. You can explicitly see that, okay, if you have a d by dt of the sum, this would be same as sum of the d by dt. And d by dt of the integral with respect to x would be same as the integral of the d by dt. So you can take that derivative inside. So I can take that derivative inside and I can have e to the tx. Now what would be the derivative of e to the tx actually? So the derivative of e to the tx is going to be first tx, and then the derivative of tx with respect to t is going to be x, because the derivative of t is t. Okay, and this is really m prime of x of t. Now in this function, if you substitute, say, 0, t equal to 0. So you're going to have expectation of 0 times x, which is equal to the expectation of x. Aha! So what conclusion you got? The conclusion that we got is that if I know this formula explicitly, I can derivate this formula and moment generating function once and substitute t equal to 0. That would be equal to the expectation of that random variable. How about if I differentiate this again? So if you're going to differentiate this again, you're going to get m double prime of x of t, and then again the derivative of the expectation is expectation of the derivative, and then there is no t in it, so you again gonna differentiate this this e to the tx with respect to t. So you're gonna get again expectation of e to the tx times the derivative of the power, which is going to be x times this x actually. So this is same as expectation of x square e to the tx. Okay, and if you compute the second, if you compute this value at 0, you're going to get this is equal to the expectation of x square. Okay, you're going to get that this is equal to the expectation of x square. So in this, if I take this function and differentiate it with respect to x, say 2 times, and then substitute t equal to 0, that would be equal to the moment, second moment actually. And hence you can generalize this inductively, and you can show that if you want to compute the nth moment of the given random variable, then what you can do, you differentiate with respect to t this function n times, okay, and substitute t equal to 0, and substitute t equal to 0, that would be equal to what you call the expectation of x actually. Okay, and moment generating function is another important thing that you always have to keep in mind actually. In other words, what is the moment generating function for the binomial random variable? What is the moment generating function of the normal random variable? What is the moment generating function for the Poisson random variable? You should know these, by heart actually, because it will make your life in probabilistic calculations very easy actually. Okay, so let's calculate some of the examples of the moment generating functions actually. Okay, moment generating function. So consider. So the first example is, okay, if x is a binomially distributed random variables with the parameters n and p, the question is, what is the moment generating function of the binomial random variable? Okay, the answer is that yes, you can calculate it easily. So for that, what we need to do, we need to compute the expectation of e to the tx. And if x is a binomially distributed random variable, this is going to be equal to, say, x equal to 0 to n e to the tx multiplied by the probability that x is x. Okay, you can assume that x represents the number of successes in n trials, where in each trial the probability of success is p. Okay, so this is what you're going to get. And if you take, for example, x equal to 0 to n, and you take e to the tx, and I substitute this value, so it's going to be n choose x, p power x, and 1 minus p power n minus x actually. This is what that you're going to get, n minus x. So if I simplify it a bit more, so it's going to be x equal to 0 to n, and I can say this is same as n choose x. I can put these powers, for example, this e to the t and p together. I can have e to the t times p power x and 1 minus p power n minus x. This is what that you're going to get. Now, if I, for example, assume this as a and assume this as b, This is really the binomial formula actually. Okay, so if I call this A and call this B, then this formula is A plus B power n. In other words, this sum, okay, this sum is going to be equal to, let me write it here, this would be equal to, okay, A plus B, P e to the t plus 1 minus P power n. Okay, P e to the t and 1 minus P power, what do you call, n. So the moment generating function of the binomial random variable is this function. So what is that function? This function is really, so the moment generating function of the binomial random variable is P e to the t plus 1 minus P times what do you call, power n. Okay, this is what it is. So we know from our previous information the first moment of this is x actually, which is, so expectation of x is np. So the question is, if we try to calculate the expectation through, for example, this moment generating function, are we going to get np? So we can get it. For example, expectation of x, if you differentiate this expectation with respect to the time, what you're going to get? You're going to get n times p e to the t plus 1 minus p power n minus 1. This is what that you're going to get times p e to the t plus 0 minus 0 actually, because if you differentiate this p e to the t with respect to t, you're going to get p e to the t, you're going to get this. So this is the first derivative. And now in this derivative, substitute t equal to 0. So if we substitute, for example, t equal to 0, what you're going to get? You're going to get n p, this will become 1, p plus 1 minus p power n minus 1 times, what do you call p? So the p and p will cancel out, so this will become 1 power n minus 1 and you get np. So this is really, n prime of x of 0 gives you, n prime of x of 0 gives you, what do you call, expectation of x. Okay. So can we calculate expectation of x squared, which matches with our expectation, okay, which matches with our previous information. Can we calculate expectation of x squared? The answer is that yes, you can also calculate expectation of x squared. Just differentiate this function one more time. Next time you need to apply the product rule, okay, and then substitute t equal to 0. You will see that you're going to get expectation of x squared, in other words, by computing the second order derivative and substituting t equal to 0, you're going to get n times n minus 1 p squared plus np minus n squared p squared. This is what that you're going to get. And if you, for example, expectation of n squared is going to be, so it is going to be n minus 1 p squared plus np. So this is what that you're going to get. And if you compute, for example, the variance of x, I know that this is expectation of x squared, in other words, n minus 1 times p squared plus np minus expectation of x whole square, in other words, n squared p squared. And if you simplify this, you're going to see that you're going to get np 1 minus p actually, which we know that this is our variance actually, So you see that really computing the moment generating function for a given random variable is really same as computing the expectation of x. I'm going to do another computation. So your task that is going to be about the normal distribution. So you can calculate the moment generating function for Poisson distribution and the exponential distribution for yourself actually. And any distribution. So if you have been given, for example, a random variable and its PDF, you can calculate easily its what do you call moment generating function actually. So let's see this. So let's first calculate the moment generating function of a standard normal random variable. Okay, the moment generating function of a standard normal. So the moment generating function of the standard normal random variable is going to be the integral from, so it is going to be obviously the expectation of e to the tz. Now e to the tz is integral from minus infinity of e to the, say, tz or maybe tx times the PDF of the normal distribution, which is e to the minus x square upon 2 over square root of 2 pi and dx. This is what that you're going to get. And what you can do then is that try to convert it into the standard form that we like actually. Okay. So this is going to be, what do you say, x square upon 2, say minus dx and dx, and say take this 1 over square root of 2 pi outside and do the completing square of this. Okay. By the way, if I wish, I can do this, that I put a 2tx here and 2 here. This is also something that I can do actually. And what if I need to do the completing square of this? I need to add t square and subtract t square. So it's going to be 1 over square root of 2 pi minus infinity to infinity e to the x square minus 2tx plus t square and minus t square and dx. Okay. I can write these first 3 terms as x minus t whole square, and this e to the minus t square, so this integral is with respect to x. So I can separate this e to the minus x minus t square and e to the minus minus plus t square. Okay. Obviously upon 2. Okay. So I can, for example, I separate this. So once I separate this, the integral is with respect to x actually. So if I wish, I can take this e to the plus t square upon 2 outside of the integral. So let's take, say, e to the t square upon 2 outside of integral, and what is going to remain inside is really 1 over square root of 2 pi minus infinity to infinity e to the minus x minus t square upon 2 and dx. This is what that you're going to get. Okay. And then I can make my favorite substitution. So I can say that, okay, let's substitute, say, y equal to x minus t. Okay. So let's substitute y equal to x minus 2t. So the dy, then derivative of y with respect to x is going to be dx. Okay. And obviously, as x goes to plus minus infinity, the y will also go to plus minus infinity. So this integral will become e to the t square upon 2, 1 over the square root of 2 pi, and e to the minus y square upon 2, and dx will become, what do you call it, dy. And if I wish, I can write this 1 over the square root of 2 pi inside. And the integral from minus infinity to infinity. Now what is this guy? Y square upon 2. This is really the PDF of the standard normal random variable. So you are integrating the PDF of a standard normal random variable from minus infinity to infinity. So therefore, the integral of any PDF from minus infinity to infinity is equal to 1 actually. So this is equal to 1. So the moment generating function that you get is t square upon 2. So mz of t is really what you call t square upon 2. Okay? And then you can also calculate that, okay, the expectation of z by computing the first order derivative and substituting 0, you're going to see that this will be 0. Okay? And similarly, you can also calculate the second order moment generating, second order derivative and compute the z square. Okay? This is what that you're going to get. Now let's get to the random variable, which is normal but with a generic parameters actually. Okay? Let's take, for example, a random variable x that has parameter, because I don't want to do the complicated calculation. So therefore, first I did calculation for standard normal, okay, and then I'm doing the calculation for general. So if x is mu normally distributed with mu and sigma square, then x is a general normal random variable. Then we know that I can write this x in the terms of a standard normal by saying that this is equal to mu plus sigma z actually, because z, you know, if you take x and divide by mu, subtract mu and divide by sigma, this will be equal to z, which is a standard normal. So x can be written as mu plus sigma z. Okay, x can be written as mu plus sigma z. What I'm saying is that I know that x minus mu by sigma is a standard normal random variable. So obviously x can be written as mu plus sigma z. And now I would like to compute the expectation of mx of t. This is same as expectation of e to the tx actually. This is same as expectation of e to the t times mu plus sigma z. Okay? Sigma z. This is what that you're going to get. And I can simplify this as expectation of e to the t mu times e to the t sigma z. Okay? E to the t mu is like a number. I can pull this out of expectation. So you're going to get e to the t mu. So what is going to remain? That t sigma multiplied by z. So if I, for example, treat this as a single quantity, let's call it t prime, then this is like expectation of t prime z. So this must be same as computing. Okay, so this is going to be expectation of mu t times computing the moment generating function of standard normal random variable at the moment t sigma. So mz of t sigma is going to be t sigma multiplied by z times e to the t mu. Okay, so this is what that you're going to get. Now I know the mz of t already. So mz of any input is equal to e to that input square divided by 2. So this would be equal to e to the mu t times e to the input, that is t sigma square upon 2. Okay, this is what that you're going to get. So if I simplify this, you're going to get, so the moment that you're going to get is really equal to, if you simplify this, in other words, if I write this explicitly here, that the moment generating function of random variable with mean mu and sigma square is e to the mu t plus sigma square t square upon 2. This is something that you have to keep in your kind of a permanent memory. Okay, this is something that you have to keep in your permanent memory, because we're going to use this a lot in the future. Okay, so this is what is the expectation of x. And if you see really that can this moment generating function can give us, what do you call, expectation and variance, the answer is yes actually. I mean, you just need to simply, differentiate this function, for example, once. So if you're going to differentiate this function with respect to mu t, so it's going to be mu plus